Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be talking about more examples related to Euler-Lagrange equation, and then towards the later half we'll start to introduce the concept of Hamiltonian via the Legendre transform. So let us start our discussion here. So in the previous module we have seen one example where we saw we had to find the extremal of this functional g of x given by 1 to 2 x dot square by 4t dt, and we saw that x1 of is 5 and x of 2 is 11, and then if we were to we found that the extremal based on these boundary conditions were x is equal to 2t square plus 3. And then let us now continue our discussion for this example. Then what we had was we had to find, the next problem says we have to check whether this function, the answer to this previous problem is a max or a min, Okay, so essentially we have to find whether j of x plus h minus j of x is so let us see this difference, j of x plus h minus j of x. So if we plug in x hat is whatever we found in the previous example, 2t square plus 3, and this is going to be 4t square. So so x hat is going to be that is going to be our j is x dot square by 4t. So we have to take a derivative of this quantity and plug it here. So derivative of x hat is 4t. So 4t plus h dot and then whole square, because we had a square here. So whole square divided by 4t dt minus integral 1 to 2 4t whole square by 4t dt. Okay, so then we try and simplify everything here. We get this is integral 1 to 2 4t plus 2 h dot plus h dot square by 4t times dt minus integral from 1 to 2 4t dt. And then we can see that we can cancel out this quantity, we can integrate this, we get 2 of h evaluated at the end points, and we know that the perturbation is such that h of h evaluated at the end point will be 0, and that is what we have. And then finally we get the remaining integral of this form, h dot square by 4t from 1 to 2 dt. Right, and we can clearly see, since time is greater than equal to 0, so this integral is greater than equal to 0, and we can quickly say that the difference of these this functional is non-negative, or what we can say from here is that x hat is a minima, right, because the difference for whatever the perturbation is always a non-negative quantity. Okay, so then let us continue for the Euler-Lagrange equation for a very specific case, that is of the autonomous system. So Euler-Lagrange equations for autonomous system. And so our integrand Well, the functional is of this form, dt, and our integrand now is a function f of x dot comma x double dot, right? Sorry, f of x dot comma x. Well, let us revise quickly. So I'm talking about the Euler Lagrange for autonomous system. And what I am assuming is, if the functional is of this form, then f is purely a function of x and x dot, right? So then if we were to write the Euler Lagrange for function of this form where t is explicitly missing, then we have d dt of x dot partial f partial x dot minus f is x double dot partial, well, let's continue with the chain rule, x double dot partial f partial x dot plus x dot d dt of partial f partial x dot, right, minus x double dot partial f, well, now we are evaluating this integral, x double dot partial f partial x dot plus x dot partial f partial x, right? And we see that this is also equal to x dot d dt of partial f partial x dot minus partial f partial x. Okay, so then we see that this particular equation, I can write this, well, we know that this is 0, right? So that's 0 here. So this is via the chain rule, and these two gets cancelled, and of course, yeah, so this is 0 because this is the our Euler Lagrange equation. So so what we have is that this particular quantity here, this quantity, if the time derivative is 0, which means that this quantity partial f partial x dot minus f, this is 0. So this particular quantity is 0. Sorry, this particular quantity is a constant, and then we call this specific case of Euler Lagrange to be Beltrami identity. Beltrami identity. Okay. So let us now look at one example for this case. So the problem I have is as follows. The functional which is given, j of x, is integral from 0 to 7, 1 plus x dot square to the power half by x dt, that lies in x greater than 0 and satisfies the end condition. The end condition x of 0 is 4 and x of 7 is 3, right? So our f is as follows. So my integrand is 1 plus x dot square by x. It's purely a function of x and x dot. So I can use my Beltrami identity, and if we do that using Beltrami identity, if we do that, we get that x times square root 1 plus x dot square is equal to c. And from here I can find that, so from here we see that square root c square minus x square is t plus d, or what I have is this equation can be rewritten as x square plus t plus d whole square is equal to c square, right? So if we were to use the initial condition, if we use initial condition which is given by these endpoint conditions here, I see that my constants can be found, and these are the values of the constant. So essentially If we plug all these values, which gives us this curve is the well-known curve. It is a circle with center 0, 3 and radius equal to 5. So, well, so that's almost the answer, except the fact that we want x as a function of t, and if we find x specifically, we see that x is square root 16 plus 6t minus t square, right? So we have x is the following. We have to take the positive value because the square root is, we have to find the value which lies in the first quadrant. Okay, so then now let us look at another case of example here. The next problem that I would like to discuss is a very famous problem of particle traveling down a curve, and we want to find the minimum time of travel, or the so-called brachistochrone problem. Brachistochrone problem. Okay, so we have two fixed points. The problem says we have two fixed points P and Q, which are connected. Two fixed points which are connected by a smooth wire, which are lying in the vertical plane. That contains the point P and Q. And a particle is released from rest. So when I say a particle is released from rest, I am giving the listeners the initial conditions. A particle is released from rest at P and slides under uniform gravity. Along the wire to Q. Okay. So the problem says what should be the shape of the wire? What shape should the wire be that the travel so that the travel is in the shortest possible time? So that the travel completes in the shortest time. So we need to find the shape of the curve. And the problem clearly specifies that we have to minimize the time. So we have to write the time functional of this integral. Okay, so the definition says time is distance divided by speed. So let's say the point, we have 2 points which are the starting and the ending point. So let us say, let us now fix the point, one of the point to be the origin. So let my point P to be 0, 0 and my point Q to be A, comma B, and let us say my time integral T of Z is from P to Q. Let us say that this is dz by V, right? So this is my distance divided by the speed is going to be the time integral, and so the time integral. Now, what could be our distance curve? The distance is the curve, the path curve between the points P and Q. So if we were to write the distance integral, this is going to be 1 plus z dot square to the power 1/2. And if we were to write the velocity now, since the particle is going from P to Q, we see that the only force acting on the particle here is the mass, which is mgz, right? And from here, the mass, which is mg, Now, which means that if we were to equate the potential energy, the potential energy plus the kinetic energy is equal to the conserved quantity of the system. So if we were to find the kinetic energy, it is related to the potential energy. So at any given point of time, the potential energy will be at a distance minus mgz, z being the vertical height the ball is traveling. And so if I equate the kinetic energy minus mgz, which is the potential energy, and initially the particle, let's say, is at zero potential energy, and the particle is already at rest initially, which is given, so the total energy will be zero. So from here I can find that the velocity here is square root 2 gz, and that I can use it in the integral, which is given by square root 2 gz dz, right? And now then we can start to integrate. Well, we can quickly see that this is an integral which only has z and z dot. So again we can use Beltrami identity, and what we see is Beltrami identity is given by f of z is equal to square root 1 plus z dot square divided by square root z, right? And from here I see that z 1 plus z dot square is 2c, right? Okay, so then I can, this is, I have already solved the Euler Lagrange. So the Euler Lagrange, after solving, I mean, of course we have used the Beltrami version. This is what it is. Then we can try and this is my extremal. We can this extremal still has this quantity z dot. We can further integrate this extremal. So if we do that, we see the following equation emerge. Remember, z dot here is dz dx. That is the rate of change of vertical distance as the particle is moving horizontally, right? So so then if we were to write the function, so we integrate this equation here. We see that x is equal to plus minus c times square root of z divided by 2c minus z, and we can integrate this dz, and what we find is, well, this is not going to be an easy integral, so we can use some trigonometric substitution. Say for example, if we use z is equal to c times 1 minus cos psi, right? And what we see is that x is given by plus minus c square root 1 minus, z is 1 minus cos psi, and of course 2c minus z is 1 plus cos psi, and that is the integral that we have to do, and the derivative of dz is going to be sine psi d psi, right? And we integrate this, and this is what. So after going through this integration, we find that x is going to be plus minus c psi minus sine psi plus d. Okay, so that is my integral here. And then, I do have some initial condition. The particle is getting released from rest. So at t equal to 0, x and z are 0. And I can quickly find that my initial conditions are that will give the value d equal to 0 and c equal to a over 2 pi. A over 2 pi. And that is where we can plug all these things to find our solution. So the solution is x is, see, we are only going to worry about the motion in one quadrant, let's say in the positive quadrant. So we will take the positive solution. So x is c, which is a by 2 pi times psi minus sine psi, and z is given by a by 2 pi 1 minus cos psi. Okay, so then we can, if we were to draw this motion in the first quadrant, this is going to follow, the motion of this particle, let's say from P to Q, is going to eventually follow a motion which is the motion of a particle on the rim of a tire. and that is why this motion is also said to be the so-called cycloid. So it's a very famous problem that psi is the angle that it makes with the positive x-axis. So the cycloid is the solution. The cycloid curve is the solution to the famous brachistochrone problem. So that is what we have shown. Now then, let us now touch upon another problem in variational mechanics, which is very nicely, taught in class 12th textbooks, in class 12 science textbooks, namely the Fermat's theorem of light travel. And we shall show that using calculus of variation how Fermat's theorem is derived. Essentially, in class 12 textbooks, people who have done basic science in high school, they are taught that when light passes through different mediums, then the light bends, and of course the time travel changes for the light to travel the same distance, but the bending is in such a way that there is a certain law which is satisfied, which is the so-called Snell's law. Everything will be written here, and I will show in the next few minutes as to how the Snell's law is derived from calculus of variations. So let us continue. So what we are trying to derive is the Fermat's principle for the motion of light, the Fermat's principle, and what we have is that we have x and y, and from here what we get is, let's say the light is traveling. So let's say we have one medium, then we have a second medium, and between each medium the light is traveling, let's say from psi 2, and then when it hits the second medium, then it will travel and have let's say psi 1 and psi 2. These are the different angles of refraction. I'm not going to go too much into science, but I'll just touch upon that. The idea is, the Fermat's principle says that when the path of the light rays, when they meet a plane of interface between two or more homogeneous media, then either it reflects or refracts such that the time taken is minimized. Okay, so let me write this Fermat's principle. The path of light rays meeting a plane, the path of light rays meeting a plane interface between two or more different homogeneous media is either reflected or suffers a change in direction, that is, it is refracted. Okay, so what I have shown in this diagram is the refraction of light, and then the whole process is according to Snell's law. This is according to Snell's law. Okay, so what we have is the Snell's law says that the motion of the light is such that if the various refractive index is given by n1, n2 and so on, then n1 cos psi, ni cos psi I is a constant of the system. Or in other words, if we were to write this statement, the Snell's law, then n1 cos psi 1, which is the angle of refraction, is n2 cos psi 2, is n3 cos psi 3, is and so on and so forth. So ni are the refractive index of each media. They are the refractive index of each media, and psi I, they are so ni's are the refractive index, and psi i's are the angle that the rays make with the positive x-axis. So psi i's are the tangent angle. Okay, so then we would like to show how this is found. So let us see how this Snell's law appears through variational principles. So the idea is as follows. We want to write down, so the idea is the light travels through various media in such a way that the time is minimized, or the time taken by the light ray at each of the media is the shortest possible. So we have to develop a time functional for this light ray problem. So let us set up the problem. So the variational Fermat's principle says that of all possible paths that a light ray takes between 2 points, the actual path is the one that makes the travel time stationary. The actual path is the one that makes the travel time stationary. Okay, so which is what we have to do. We have to minimize this functional. So minimize the time functional. So the idea is we have the integral is for at any given point, the time functional will be ds over the velocity of the light inside a given medium. So velocity of the light inside a given medium will be the speed of light in vacuum, which is a universal constant c, divided by the refractive index of the media, which is also a function of y. Right? So now let us rewrite this integral. So this integral is n of y times 1 over c times ds. ds is under root 1 plus y dot square dx. Right? So that is my curve. That is my curve integral, and we see that. So what we have is, from here we can write down that again c is a constant. It's a universal constant. So now we see that this integral only contains the integrand of this integral only contains y and y dot, which means that the explicit appearance of time is missing in this integral. So we can use Beltrami identity here. So if we use Beltrami identity, we are going to get that the Euler-Lagrange solution will come out to be n of y times 1 plus y dot. So I'm just writing the final answer. The listeners are going to go home and find the Euler-Lagrange equation. 1 plus y dot square 1/2. This is a constant, and if we substitute y dot equal to tan psi, if we substitute here y dot equal to tan psi, then we can quickly find that the Euler-Lagrange equation gives us that it is n of y times cos of psi is equal to a constant. Right? So n of y times cos psi is equal to a constant, and that is what we have in Snell's law. Okay, Snell's law. That is a very quick application of the calculus of variations, which gives us what we have already seen in class 12th or basic science for high school. That is the Snell's law. Okay, so then I would like to start our discussion on Hamilton's principle, but I think I'm all out of time for this module. This is going to be continued in the next module. Thank you so far for listening.